Welcome to this presentation on the design of a flexure-based, low-frequency Foucault pendulum. In this presentation, we will first explain the principle of the Foucault pendulum. We will then show that the Foucault pendulum can be faithfully modeled as an isotropic, planar, 2-degree of freedom oscillator, and that therefore other oscillator designs present the Foucault effect. We will also explain that unwanted parasitic effects are present in a Foucault pendulum and how they can be reduced. We will then move on to the contribution of this presentation, which is a novel design for one of these isotropic oscillators. We'll then explain how its stiffness can be adjusted, which will enable its frequency to be reduced. This aspect is most interesting for Foucault pendulum experiments, as lowering the frequency reduces the parasitic effects. The Foucault pendulum is a famous physics experiment first led in 1851 by the famous French physicist Léon Foucault, which is a direct demonstration of the Earth's rotation. It consists of a spherical pendulum in which the mass is pulled to the side and then released with no initial velocity. The mass then oscillates back and forth in a straight line. However, I don't like to say it goes in a straight line since the motion of the mass is restricted to a sphere, so I prefer to consider the plane that contains these oscillations. Following the principle of inertia, this plane of oscillation will remain fixed in respect with an inertial frame. However, for an observer on Earth, the plane of oscillation will appear to slowly turn. If we look a bit closer at the usual equations justifying the Foucault pendulum, they neglect the vertical motion and assume a linear restoring force. The Foucault pendulum can be faithfully modeled as a 2-degree of freedom planar oscillator, as the vertical displacement can be considered negligible, and therefore all other planar isotropic 2-degree of freedom oscillators also present the Foucault effect. The rotation of the Earth is not the only effect acting on the oscillator. There are two main parasitic effects which can easily mask the rotation of the Earth. The first is the isotropy defect, which is due to errors in the symmetry of the mechanism and appear during manufacturing and assembly. This defect causes initially linear orbits to degenerate into Lissajous figures. The second is the area effect, which is due to the fact that the oscillator is not perfectly harmonic. The consequence here is that if an orbit is slightly elliptic for whatever reason, this ellipse will precess. Both of the defects can easily mask the Earth's rotation, and they increase with the oscillator's frequency. This is the reason why short Foucault pendulums are difficult to make, and why museum Foucault pendulums are typically at least 7 meters tall. For this reason, we propose a design to reduce frequency without increasing oscillator size. The new oscillator we proposed is based on flexures, which provide both the desired kinematics as well as the restoring force. Indeed, flexures act as springs which bring the mass back to its neutral position. The design is based on the parallel leaf spring stage, in which the mobile mass is linked to the ground by 2 parallel leaf springs. This mechanism has a translational motion along the x-axis and therefore has only 1 degree of freedom. To enable translation along both the x and y-axes, the leaf springs are replaced by flexible beams with a circular cross-section, which can bend in all directions. A third beam is needed to be added to prevent rotation around the x-axis. So we have 3 beams here, here, and here, and the mobile mass consists of this triangular part, this circular bar, and this square part at the base. The design therefore resembles roughly a camera tripod whose legs are flexible. If we look a bit closer, we notice that not only can the mechanism move in translation along the x and y axes, as shown in these animations here, in which only the 3 beams are represented, but there is an additional degree of freedom in rotation around the z-axis, which we do not want. We ensure that this mode is not excited by having its frequency be much higher than the frequencies in translation. The center of gravity of the oscillating mass is located at mid-height of the flexible beams. For this reason, the oscillating mass consists mainly in this long bar. Moreover, this shape reduces the inertia in rotation around the z-axis, which increases the frequency of the unwanted degree of freedom in rotation. As mentioned before, the oscillating mass has a square-shaped part at its base. This part serves as a target for a first set of distance measuring lasers, which determine the x and y position of the oscillating mass. There's also an extra set of lasers which determine whether the unwanted degree of freedom in rotation is excited or not. The translation of the parallel leaf spring stage isn't exactly rectilinear. Assuming small deflections, the trajectory is a parabola due to beam shortening. The same effect is present in the 3-beam oscillator, in which the movement is restricted to a paraboloid. This is in fact the key aspect of the oscillator, as it enables the overall stiffness and frequency to be reduced by increasing the mass. Let us explain this in more detail. Two forms of potential energy are present. The first is the elastic energy stored in the beams. As the elastic energy follows Hooke's law, the stored energy is quadratic with respect to the displacement. The second is gravity. Since the mass is at its highest in the neutral position, the gravity will try to move the mass away from this neutral position. This is identical to having a ball placed on top of a hill. Moreover, since the motion is a paraboloid, the energy is also quadratic with respect to the displacement, but of sign opposite to the elastic energy. The total energy, which is the sum of elastic and gravitational energies, is therefore also quadratic, which follows Hooke's law and behaves like a spring. By increasing the value of the mass, the overall stiffness is reduced, which lowers the frequency. This is the key aspect that reduces the parasitic effects in the Foucault experiment. A prototype is currently under construction, and after assembly, the isotropy defect will be reduced in order to try to detect the Earth's rotation. This is a well-known challenge in constructing short Foucault pendulums. The first functional Foucault pendulum was only built over 20 years after its invention by Kamerlingh-Onnes in his 1879 PhD thesis. He later won the Nobel Prize for discovering liquid helium and superconductivity. Kamerlingh-Onnes had a method to reduce the isotropy defect, in which he would observe the trajectory of this pendulum and then file the mass at the right place to correct the defect. We will inspire ourselves from his method by measuring the frequency in all directions to then file the beams to reduce their stiffness in the direction in which the frequency is highest. Concerning the dimension of the prototype, it will have 500 millimeter long beams with a diameter of 1.8 millimeters, and the mass will weigh 900 grams. This will lead to an initial frequency of 0.5 Hz. Additional parts will then be added to increase the mass and lower the frequency. To which extent we will lower the frequency has yet to be determined. In this presentation, we've described the Foucault pendulum and its parasitic effects. We have shown a new oscillator, which is a transportable version and does not require a tall ceiling, and whose stiffness can be lowered to have a frequency comparable to a 7-meter pendulum. Future work includes fabrication and adjusting of the isotropy defect, as well as the analytical solution for the airy precession. Indeed, as the Lagrangian of this oscillator differs from that of a spherical pendulum, its airy precession will be different. Thank you for your attention.